Hi, my name is Chris Assad. I'm a robotics engineer at the Jet Propulsion Laboratory, or JPL. And today I'll talk about the JPL BioSleeve, a wearable hands-free gesture control interface. As robots become more everyday items and become more autonomous, we need better ways for humans to interact with robots. So what we have today is an interface that you wear on your arm that measures signals from your muscles and from your motion. It tells you what your hand is doing. So you can recognize hand gestures. We can do about 20 different hand gestures recognition, gestures of the wrist and the fingers, and larger gestures of the arm. And from these natural gestures, we can recognize the gesture, map it to a command, and send it to a robot. The innovations here are we're mixing different gestures. We're using some newer machine learning methods to do the recognition, and we're trying to make it wearable. So this is a sleeve you just pull on, calibrate, and go. And then you can see a comparison to the state of the art. This is the number of classes, number of gestures you can recognize, and this is over time. And we're comparing ourselves to what's been reported in the literature for EMG from forearm. And we're doing, this was a year ago already, we're doing better than everyone that we could find in terms of number of gestures. So in the past, we've controlled several different robots. We've controlled Dragon Runner from Kinetic North America. It's a bomb disposal robot. We've controlled the JPL RoboSimian, the JPL surrogate robots. We controlled an arm built at JPL with a prosthetic hand. And we've controlled iRobot Landroid and, of course, Sphero's BB-8. So we're going to show you two demos today, one with the iRobot Landroid and one with the Sphero BB-8. You can see from the picture we have 24 EMG sensors on the forearm measuring muscle activity in the forearm that control your fingers. And then we have a few IMUs. Normally we have 3, today we only have 1. And then we have a processor board up on the forearm. And now this can all be shrunk down and embedded in clothing in the future. So the applications for this, for NASA, we're interested in having astronauts on EVA controlling remote robotic assistance. So for instance, an astronaut walking on Mars could wave to a robotic rover, say, move there, go there, pick up that rock, and we can already do that with our rovers. And we've also tested our interface inside of an EVA sleeve, and it still works. Other applications include interfaces for prosthetics. This was meant to be a controller for a prosthetic hand, and interface for force control for exoskeletons. So these are the type of sample gestures here. We've done up to 20 gestures at a time for static gestures of the wrist and fingers, and we've also done 10 dynamic gestures of the arm, mainly using the IMU data. So we can do about 30 gestures. The 20 EMG-based gestures we can do with accuracy of about 95% from just a 3-minute calibration at the start. And it usually holds about 90–95% for an hour, and then you have to retrain. So we're working on getting it to the performance to last longer without a retraining, and to get a higher accuracy, of course, on the gesture, and increase the number of gestures. So today we trained for go straight, turn right, turn left, back up. This is supposed to be stop. And then we had a do your dance gesture. So we can change that gesture set. We can also change the command set. So thanks for watching the demo. My name is Chris Assad. I'm from the Jet Propulsion Laboratory. You can reach me at chris.assad@jpl.nasa.gov.